Alright, so let's talk about the game model, the generative adversary network model architecture. So the game model actually is designed based on a game between the generative model and the discriminative model. Inside the game, we will have one generative model to generate some data instances which looks very real. Then the discriminative model will be serving as like a judge, right? It will be differentiating the true data instances from the real world data set versus the fake ones generated by the generative model. And let's have a look at the generative adversary net. The game will be a game between the discriminative model and the generative model. Inside the game model, we have one discriminator and one generator. We can denote the discriminator as D and the generator as G as shown here. So the discriminator will distinguish the data instances sampled from data distribution, the real world data distributions, or generated by the generator, like G as shown here, right? As to the generator, like G, it tries to cheat the discriminator by generating data instances that are as hard as possible to be identified by the discriminator. What do we mean by hard to be identified? We want to ensure that generated instances will be very similar to the samples we get from the real-world data distributions. In other words, there will be a min-max game between the discriminator and the generator as shown here. Then a min-max game between the discriminator and the generator will be able to help train a greater image generative model. And so this is some high-level ideas. Then let's have a look at the model architectures. So in the game model, we have two main parts, the generator and discriminator. And we also have a real-world data set, this part, right? In this page, we show you the example about data set, which is about some famous people faces, right? This data set, these are images. And these are all the real world, the real data set, right? And then, for the generator, it will be try to generate some fake images, right? These are labeled as real, and this generator will generate some images, and they can be labeled as fake, right? And how can we generate some fake images? By giving the generator with some inputs. These inputs are normally some random numbers we generate from some distributions. We name it as noise as shown here, but these are all random numbers, you can see in this way. Given some random numbers, we feed them into a generator. Then this generator will generate the images, these fake images, right? So by feeding these images, even though we label them as fake, as well as real-world data images into the discriminator, then we will be able to learn both the discriminator and the generator by defining some nodes. Terms. The nodes term covers both the discriminator nodes as well as generator nodes. What is the discriminator nodes? So, if for the discriminator, if it can distinguish the real images from the fake ones, then they will do the correct identification, right? In other words, they have no nodes at all. So the discriminator will be responsible for classifying the real images from the fake ones to define loss term, right? And they want to identify which one is real and which one is fake. And how about the generator? For the generator, how to define its nodes? It's not rely on the discriminator. In other words, if we generate a very good image which looks very real, can cheat the discriminator. If so, then we can have a very small nodes. Otherwise, if we generate a very bad image which is very different from the real ones and the discriminator can classify them correctly, then we will have larger nodes, right, for the generator. So you can see, for the discriminator, its node is defined by its classification from the real to the fake ones. However, for the generator, its node is defined by the quantity of the images it generates. If the quality of the image is very good and it looks very real and can cheat the discriminator, its nodes will be small. Otherwise, if the quantity is very bad, then its nodes will be larger, right? So the generator nodes term actually defines rely on the discriminator as well. So this is general framework for the game model. We have the real-world data inputs. We label them as real. We also have one generator. The input will be some random numbers. They can generate some fake images. We label them as fake. We feed both real and fake images into the discriminator and to define the loss function for both the discriminator as well as generator. So you may wonder, how can we define the discriminator as well as how can we define the generator? We have different ways. The easy way probably is we can define both discriminator and generator as MLP actually. If so, then we can provide you with more detailed information about the architecture of the game. So here, if we define the generator and the discriminator as MLP, multi-layer perception models, then we can show the architecture of the GAN model in this way, in this page. So how to read this picture in this page? So this part is about the real-world part. The first part. Given the real-world data images, we feed them into the discriminator, right? And to define loss functions. This part. So given one real image, we can feed it to the discriminator, right? Which will be called discriminator, the D as shown here. And this discriminator model will try to identify this one to be a real image. We can label it as 1, as a positive 1, as shown here, right? If so, then it will be a real image. On the other hand, besides discriminator, we can also have one generator, right? This generator will receive some inputs from random numbers, right? We can have one random number which is from some distribution as a noise vector, right? By feeding this random number, this noise vector Z, to a generator, the generator is also one MLP as shown here, right? So via the MLP, we can generate one image like this one, right? X prime as shown here. This one is a fake image, right? We can further feed this one to the discriminator, and we will try to cheat this discriminator, right? In other words, we aim to project this image, this fake image, to a 0 enabling state. So you can see, right? The discriminator will receive inputs from both the real data, real images, as well as the fake ones are generated by the generator, right? And the discriminator try to differentiate them from each other. In other words, they want to classify them into different classes or different labels. However, for the generator, they receive inputs from the noise or the random numbers. They try to generate some of the fake images, which will be fed as input for the discriminator. Okay, so we can define both the generator and the discriminator with the MLP model we defined before, as shown in this page, and then we can train the model. And you may wonder, how can we really define the loss function? Because before we just provide you with some high-level ideas, and then let's come to the loss function defined for the GAN model. So remember, this GAN model we define a min-max GAN between the discriminator and the generator, right? So for the discriminator, we want to ensure they can distinguish the real data from the fake ones. And we can define loss function for the discriminator, in this way. So you can see in the loss function we have two terms. The first term is about expectation, right? And the second one is also expectation. However, the data we have are from different sources. For the first term, we have X from the real world data set, right? This X is sample from the real data. And for this one, we want to maximize their probability or the scores, right? We define this one to be a score by the model. And we want to maximize this term. This is not dx denoting the score we can obtain from this discriminator on the true data instances. We want to maximize these scores, right? However, for the fake data instances, we can generate from the generator, and we want to ensure the discriminator can distinguish it, right? In other words, we want to minimize each score instead. So for the data instances, we can obtain from the generator, right? So here we have Z to be the noise, right? To be the noise. So by feeding this Z noise into the generator, we can have one image input, right? For the discriminator. The GZ will be the fake image we feed into the discriminator. However, for this one, we want to minimize its score, right? Therefore, we can define its score as 1 minus this DGZ. So by maximizing this term, in other words, we'll minimize the score for the discriminator on the fake image instances. We have 1 minus here. This is how do we take a look at from the discriminator perspective. Right? And how about the generator? Generator want to minimize. For the generator, they want to ensure the quality of the image they generate from the noise input. They will be looks very similar to the real world data distributions. In other words, by minimizing this term, for example, as shown here, right? So by minimizing this term for the generator, in other words, this discriminator will make a mistake, right, for their images generated by the generator. So in this way, it will be a min-max GAN between two of these agents or these models, G and D, as shown here. So I know it is very hard for you to understand this formula if you have never learned the game theory before. So another easier way for you to maybe look at the formula or loss function as shown here is to illustrate the learning process. So for this kind of min-max functions, the solution will be an iterative learning process with one of the model fixed, the other one will be, optimize it. Then we can do it in the reverse way. In this page, we also show you the iterative model learning process. Let's assume, because here we have two models, G and D. If we have this G fixed, so by fixing this G, in other words, this GZ, this one will be a constant, right? Because this G is fixed. And this GZ will be a constant. With this G fixed, then we try to optimize for D, right? Because here we have min-max. If G is fixed, then we just remove this one and we maximize this function, right? So we maximize for the D. Its function will be the first term as well as second term, right? The first term is a score for the real data instances. The second one is a minus score for the figure instances, right? Because this one is a constant here. So by maximizing this function, these two terms together, then we'll be able to learn the discriminator. Right? This is the first step. Another step will be we have a D fixed, and we want to optimize for G, this generator. By fixing this D, this max D will be a constant here, right? In other words, this first term will be a constant because this D is constant, right? We can remove this term, and when we're optimizing for the generator, we can focus on the second term instead. So for the second term, it will be min J on some functions, right? If this D is fixed, in other words, this D mapping will be a constant. We are optimizing this generator by the second term only, right? We are optimizing by the second term only. So for the second term, by minimizing this function, this term, in other words, so for the G, if it can cheat the discriminator, in other words, for DGZ, this term will be a very large number, right? It classified to be a positive instance, as shown here, right? If so, in other words, if a very good G, which can cheat the discriminator, it will achieve a very small number and it can beat our expectation by minimization, right? So by minimizing this G, this function here, we can learn a very good generator which can cheat the discriminator. And we can do the optimization of these two models, iterative and tier conversions. So each model will be selfish. They try to optimize their pair of functions. So for the discriminator, they try to maximize this term, and for generator, they try to minimize this term instead. And by this iterative updating process, we can converge to a stationary state, which will be very similar to the solution as shown here, right? If we can converge finally, then we can get the solutions for both of these two agents or these two models. In this way, we can learn this game model and by this iterative learning process among the generator and discriminator. Okay, so this is a game model architecture together with learning process and loss functions.